Hello students, in this video we'll discuss several important classes of matrices which you'll see further on in our study of linear algebra. So the first class of matrices we'll consider are the trivial ones, are zero matrices. So zero matrices have this notation. So zero matrices just look like 0 m by n, and this is a matrix of all zeros. All zeros, and of course this is an m by n matrix, And so, of course, zero matrices can come in all sorts of shapes and sizes. So, for example, I could have a zero matrix like this. That'd be one example of a zero matrix. I can also have a zero matrix like this. That's another example. I can have a zero matrix like this. So, in other words, it doesn't have to be a square matrix. It can be of any dimension. So that's sort of the easiest case. We have identity matrices. Now, these have to be square matrices. So we'll call these IDN. N by n. This is going to be a matrix 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, all the way down to a row of 0, 0, 0, 1, 0, and then 0, 0, 0, 0, 1. That's the n by n identity matrix. So examples of these matrices are the following. I have this one over here. That's a 2 by 2 identity matrix. Over here, this is a 3 by 3 identity matrix. We'll do one more. Here's a 4 by 4 identity matrix. So in other words, for identity matrices, you have ones on the main diagonal and zeros everywhere else, right? So one thing to note about these identity matrices is that the rank of this sort of thing over here, so the rank of this identity matrix, the rank of the identity, n by n, is n, because there's exactly n leading ones in here. The rank of these zero matrices is exactly equal to 0. There are no leading ones in this thing over here. So the rank of the identity is equal to n, the rank of the zero matrix is equal to 0. Now, let's talk about some more terminology behind terms of these matrices. So as I alluded to earlier, I said this identity matrix has ones along the main diagonal. So that term over there, the main diagonal, so for matrix A, which is Aij, where both I and j go from 1 to n, we say that Aii is the main diagonal. We're going to say that the diagonal above that is going to be called the superdiagonal. That's a superdiagonal. Okay? So, of course, the superdiagonal, what? You know that the column is one bigger than the row. So the column is going to be one bigger than the row. So A, I, and then I plus 1. So that's my row, and my column is one more. So for example, if I look at one, it's like a 1, 2. So 1, 2 is definitely on there, is the superdiagonal. So the superdiagonal. And then, of course, if I look at one below that is going to be called the subdiagonal. That's going to be called the subdiagonal over there. So A, that's when the row over there, the row is 1 bigger than the column. So A, I plus 1, comma I, is the subdiagonal. Subdiagonal. Okay? All right, so these diagonals play an important role in the study of matrices, right? And so let me give you two other classes of matrices which are very important in our study. The first matrices are going to be matrices of Hankel type. Well, so what are Hankel matrices? I'm going to illustrate Hankel matrices by example. So for a Hankel matrix, I'm going to draw, here's an example of a Hankel matrix. I'm going to have an A, then a B, then a B, then a C, then a C, then a C, then a D, then a D, then an E. Okay? That's an example of a Hankel matrix. And what do you notice about Hankel matrices? For these Hankel matrices, well, let's call this matrix over here H for Hankel. Then one thing you can immediately notice about these Hankel matrices is that H transpose, if I change the rows and column, look, the row and the column are the same. The row and the column are the same, and the row and the column are the same. So H transpose is equal to H. So these Hankel matrices are symmetric matrices. They're symmetric, which is beautiful. And also, what can we say about these Hankel matrices? These Hankel matrices are constant along these are not called diagonals, these are called anti-diagonals. So the anti-diagonal over here, that's an anti-diagonal. Okay? So Hankel matrices are constant along the anti-diagonals, so that's an important class. Of course, we can do more examples. If you want to do like a 4 by 4 example of a Hankel matrix, you could do something like this. You could say 1, then 2, then 2, then 3, then 3, then 3, then 4, then 4, then 4, then 4. Then let's say 5, then 5, then 5, then 6, then 6, then 7 is another example of a Hankel matrix. This is also a Hankel matrix. They'll be very important in our study of matrices with very important properties later on. And then there's sort of the exchange version of these Hankel matrices, and the exchange version of these things are called Toeplitz matrices, and these are also going to come up later on in our study, these Toeplitz matrices. These come up a lot in analytic function theory, Toeplitz matrix. So these are not constant on the off diagonals, these are constant on the diagonals over here, right? So for a Toeplitz matrix, let's give you an example. We'll call this matrix over here T. And what I'm going to do is I'm going to say this is going to be a, let's say a 2, a 2, and a 2. Then I'm going to have a what? Then I'll put a 3 over here and a 3 over here, a 4 over here, a 5 over here, and a 5 over here, and a 6 over here. That's an example of a Toeplitz matrix. And Toeplitz matrices are constant along the what? Now these things are constant along the diagonals, right? So over here we have the main diagonal. The main diagonal is all 2's. We have the subdiagonal of 3's, the superdiagonal of 5's, and so these Toeplitz matrices are constant along the diagonals, right? So T is constant along diagonals. Every diagonal, not only the main diagonal, but all the subdiagonals and all the superdiagonals, okay? And so if we can do more sort of a more abstract one, these ones are not necessarily symmetric over here because I have a 3 over here and a 5 over here, so note that these are not necessarily symmetric. So T is not equal to T transpose in this case, okay? Great. So what would they want? Another one be more generally, let's look at this T tilde. So it has to be constant on diagonals. So generically you can say A. Then we can have a B, then a B, then a B, a C, then a C, a D, an E, then an E, then an E, an F, then an F, and then a G would be an example of another Toeplitz matrix, right? And so again, as long as if B is not equal to E, then I don't necessarily have symmetry over here. So oftentimes in the study of analytic function theory, we're interested in these properties where we have either a constant subdiagonal or a constant superdiagonal, and those will give us very special properties in terms of recurrence relationships in further videos. Thank you very much.